Let us start this lecture with a thought process. Excellence can only be achieved through ceaseless and mindful energetic actions. And in the last lecture we are talking about equilibrium compositions and how we will have to attain the equilibrium, which is important for life also, so also for chemical equilibrium. What we did, we took some examples. Now today we will be looking at how systematically you can do, right. So can anybody recall how we can develop a procedure for determining equilibrium composition? Right, in the previous example I have given, what is that? 1 mole of O2 is going to O. Let us say I will take a system methane and air, right, and I know, okay, let us say equivalence ratio 1 and let us say some temperature 1000 Kelvin and atmosphere pressure 1 atmosphere pressure. Then how I will find out equilibrium composition? What I will have to do? Are you getting? In the example what I took is a very simple problem, it is given everything almost, you can say, but here how we will do? That means a question might be coming to your mind, so what are the species which will be there at equilibrium? Is that question coming to your mind or not? See, what are the species will be there? Is it only CO2 and water and nitrogen? No, certainly no. There will be n number of species, like you can say CS3, CH, CS2, COH, OH, H, water, carbon dioxide, carbon monoxide, nitrogen, NOx, like NO, NO2, I mean n number of things, right. That means I will have to identify the certain species which may be important for my calculation, okay. How to identify is an art, okay, and also what is your requirement. Art means definitely you will have to choose, let us say for methane system, carbon dioxide, you will have to choose, yes or no. You will have to choose water, you will have to choose nitrogen, right, for methane air system. There is no doubt about it, I mean absolutely no doubt, but you will have to choose CO naturally and H, OH, right, HO2, CS3, CS2, because CH4 is there, so therefore these are things will be supposed to be there, and there are several other species, whatever you want you can choose, right. That means first I will have to identify probable equilibrium species, right, okay, and then after identifying that I will have to identify the equilibrium reaction schemes, that is very important, right. How to choose and other things also very important, because whatever is known you will have to choose, for which data is available, for example the Gibbs free energy, then you will be choose. Then find out equilibrium constant, right, because I will have to find out what is that Kp, and strike a balance for elemental conservation, right, and strike overall mass conservation, and then solve all the equations by iterative method. I can give example, one example in Newton-Raphson method, there might be several other numerical methods are available, right. A question might be coming to your mind, why you will do that? Because just now we solved an example which is a quadratic equation, very easy to do that, right. If quadratic equation comes, whether we will solve? If it is, and keep in mind that is only one equation, right. So therefore quadratic equation you do, and although it is nonlinear, right, but still you can solve that. Now to illustrate this point I will take an example, right. In this example 3 moles of hydrogen are reacting with 1 moles of oxygen at 1000 Kelvin and pressure 1 atmosphere. and what we will do, determine equilibrium products, right. So, if you look at what is happening, I am saying 3 moles of hydrogen reacting with 1 moles of oxygen going to the products, right. Of course, what will be the product? What will be the product? That means, first I will have to, step 1 is what? Step 1, if you look at step 1 is identify the probable species at equilibrium. So, what are those species? Definitely N S2, right. Sorry, okay, NS2, right. Then definitely will be oxygen, then N water, what else? O, or I can say H, right, NH, H, right, plus NO, O, plus NOH, OH, right. Let us say we will take this number of species, okay. Let us say I can take any more numbers also, right. But this case, these are the probable. OH is basically how many species are there? If you look at, hydrogen is 1, right, and this is 2, this is 3, H is 4, this is 5, this is 6, right. Okay. Now, step 2 is what? Step 2, identify equilibrium reactions. So, when we are considering, we will be considering what is the elementary reactions, okay, possible elementary reactions. What do you mean by elementary reaction? Might be, a question might be coming to your mind, right, where number of bond will be broken or formed is very less, right, that we call it. I will be discussing that little. So, let us consider, because we are getting H, right, and I can say that H2 is going to 2H, right. Similarly, I can say O2 can going to 2O and H plus O going to OH and S2 plus O going to S2O. So, this is basically equation 1, this is 2, this is 3, this is 4, right. Are you getting? So, that means all species are coming here or not? H is coming, O is coming, S2 is coming, O2 is coming, total 4, and OH is coming 5 and S2, total 6 species are involved in that. That means, I do not need any further chemical reaction to be considered for this finding out for equilibrium composition, right. And step 3 is what? Like find out equilibrium constant. So, what we will do? We will basically find out equilibrium constant. So, for example, if I say for equation 1, I will say this is Kp1. For equation 1, I am saying Kp1. What it would be? It will be x, I can write down xh square xh2, this will be p by p naught, what will be 2 minus 1, is not it? If you look at the formula I had derived for your arbitrary reactions, right, it will be, you can use that, or you can use the terms of partial pressure and then convert that, any one of them. So, in this example P is what? 1 atmospheric pressure, and this P naught, or I can say this is P atmospheric pressure, right. That means this will be always 1, this will be always 1 in this example. Are you getting? That means P by Pa is 1 in this example, is equal to XH square by XH2, right. Can I not say 1 is equal to what? E, right, delta G T naught divided by RUT. So, I can write down 2 G H, right, T naught minus this will be 1. So, G H 2 T naught divided by RUT, and these are known, I can get from the table corresponding to what? Corresponding to this temperature 1000 Kelvin. That means these values are known, RU is known, T is known, right, T is equal to 1000 Kelvin, right, and from table I can get these values. Okay. I will not do that, right, but I can get. So, let us say this is my equation 5, right. Similarly, I can find out Kp2 will be XO2 by XO, O means atom, O atom square divided by XO2 is equal to, similar way should I write down, or let me write down, next I will not write down, okay, minus 2 G naught T, or I should be bracket, minus GO2 T naught. Similarly, XP3 XOH, right, by XH XO, this I can say this is 6, this is 7, because this will be known, right, this value is known, this value is known, because I know these values. So, I know Kp2, similarly Kp3 is also known, yes or no, are you not getting? Kp3 is nothing but from the delta G naught T naught divided by RUT. So, I am getting this G of the species at particular temperature from the table. So, therefore, Kp3 is known, and Kp4 XS2O XS2XO, yes or no. So, this is your 8. Now, if you look at basically 5, 6, 7, 8 equations are there, through total 4 equations. How many unknowns? Unknown 6 equations till now 4. That means I need to have 2 more equations to solve this thing, yes or no, right. So, then we will have to go for the step 4, we will have to go to the step 4 and step 5 to get another 2 equations, right. So, step 4, right, is it step 4? Strike an elemental balance, right. That elemental balance, if you look at moles of elements, we will have to do. What are the elements are involved in these reactions? What are the elements? H and O, right. So, let me write down also what we did, that is 3S2 plus O2 going to NS2 S2 plus NO2 O2 plus N water plus N H plus NO O plus NOH. Oh, this is looks to be actually N, okay, this is N, not eta, and OH. So, given, if you look at what are the total number of H moles are given, NH, if I say NH is the total moles of H is equal to what? 6, because 3 moles of hydrogen, right, 6, and NO, total moles of O is 3. Is it 3 or 2? Because 1 mole of oxygen, right, it is 2. So, we will have to do a elemental balance, right. So, what I will do, H, what is that? If you look at, right, what I will be doing, 2 NS2, right, 2 NS2, right, plus, where is that, here, plus 2 NS2O, because it is there, right, and then because left hand, this is we are looking at the product side, okay, right, and then this will be NH, only one is there, then it will be NOH is equal to what? NH, yes or no? Total number of moles in the product should be same as whatever there in reactant. Similarly, O, I will get 2 NO2, right, and N water, because this is 1 O in the product and this is 0 because there is no O, and in this case it will be NO plus this will be NOH is equal to NO, right. Let us say this is equation A, this is B, what else say? I will just divide it, right. Should I divide? What I will get if I divide? That means NH by NO I know, and then I will find it, but these are in the moles, but I need to express in terms of mole fraction. So, that what I will have to do? I will have to divide this equation with N total number of moles, right. And if I divide by this all together, right, N total, similarly N total divided by N total, what I will get? I will get 2x S2 plus 2 x water plus XH plus XOH is equal to NH by N total. Similarly, from this expression I can get 2xO2 plus x water plus XO plus XOH is equal to NH by N total. If I say this is C and D, now I will divide C by, right, dividing equation C by equation D, we will get what is that? 2xH2 plus 2x S2O plus XH plus XOH divided by 2xO2 x plus XO plus XOH is equal to NH by, this will be NO, okay, there is an error here, NO in equation D, NO, and total cancel it out, this will be equation 9. Now, right, because this is known NH is known or not? NO is known. So, therefore, I mean these are unknown and you will have to evaluate. And what will I do now? Step 5. Right, close the equations. Basically, you will have to balance. What is that? Summation of mole fraction equal to 1, right, because these are 5 equations and 6 unknown. So, we will have to close that equation. For that, we will have to do this, and this is equal to x S2 plus x O2 plus x water plus x H x O plus x O H is equal to 1. This is 10. That means, if you look at, right, these equations has to be solved, like equations, what is that? 5, 6, 7, 8, 9 and 10 are to be solved simultaneously. Right. See, if it is linear equation, you know how to solve, okay, but if it is non-linear equation, it will be difficult. Why it is non-linear equation? Can anybody tell me why? You will have to go back to the equation 5 and 6. See, if you look at, this is x H square, x O square, right, and x H x O, right. So, therefore, these are non-linear. So, for that solve, right, these equations are non-linear in nature, hence iterative techniques, right, iterative techniques like numerical methods can be used, and the one is, you can say, Newton Raphson method can be used, right. So, if you look at, it is not that easy to really do this. You are talking about if the temperature is known and the equivalence ratio or the fuel air ratio is known, then you are finding out compositions, right. Now, imagine in adiabatic temperature is not known, temperature is not known. When you are talking about fuel air mixture, you do know the temperature, you do not know. Now, how we will have to get this composition? These are all interlinked, because temperature is dependent on this composition. Why? Because Gibbs free energy is dependent on the temperature, and this Gibbs free energy, that Kp values will be different, because Gibbs free energy is different. So, Kp values will be different. So, therefore, the composition will be different. Are you getting? Now, you will have to do that. How we will do? It is a very difficult thing, and then you will have to do iteratively. Now, we are going to see how we are going to do that. We will have to determine how to devise a procedure for determining equilibrium compositions, that means mole fraction of species, and also adiabatic temperature, both are interlinked. Okay. So, I will just tell you the procedure. Given that pressure is given and the unburnt temperature is given, it need not to be 298 Kelvin, it may be 600, it may be 500, whatever it may be, right. It may be 298 Kelvin, and fuel oxygen types, whether it is hydrogen air, methane air or propane oxygen or kerosene oxygen, you know, like that is to be also known, otherwise you cannot do. And what is the fuel oxidizer ratio has to be given. Is that clear? This has to be given. Now, what you will do? You will have to assume a adiabatic temperature, because we have already seen in the last procedure that temperature should be known, then only I can find out composition. So, I will assume a T adiabatic temperature. Then compute the equilibrium composition at a particular pressure and adiabatic temperature, that we have already seen how we will have to do that iteratively. Okay. That is also iterative. This is a iteration inside iteration, you know, you will have to do that now. Okay. So, then what you will do? You will estimate the adiabatic temperature by, this is your sensible enthalpy, right. This is your sensible enthalpy of the product and this is the sensible enthalpy of the reactant. Are you getting? Of reactants. This is sensible enthalpy of product. Of involving various species. Ni will be various species. It can be if it is a product, it will be, if I consider methane, there might be 20 species or the 10 species, at least 15 species kind of things, right. So now, and if it is a reactant, of course, if it is a methane air, only methane, oxygen, nitrogen, right. Reactant will be easier to handle, but product will be several of them. Now once you this thing, because you have already find out composition, that means you know this Ni, right, or in terms of moles, fractions, then you can do very easily, and this is nothing but your heat of reaction. This is heat of reactions at STP, right. And then by this you will find out T adiabatic, because you will have to integrate. Keep in mind this Cp is a function of temperature, right, that you will have to plug in and then integrate. That integration is not that easy. The way we did the example is not the way, okay. There you will have to integrate, because the various temperature range you will have to use different Cp values. I had shown that, I think, right. And then you will have to find it. Now if this T adiabatic, right, whatever you calculate, right, this is the calculated one, calculated from here, from this you will get T adiabatic, and minus T adiabatic gas, let us say you guess something 2000 Kelvin, now you are getting 2400, let us say. That means this is not acceptable. If it is a small value, let us say 1% error, right, then you will say accept. Let us say if it is the assumed value is 2400, but the calculated value is 2410 Kelvin, then okay, fine, because this is okay, you need not to go again, it will be stopped. Otherwise what you will have to do, you will have to find out a new adiabatic temperature, that is equal to T adiabatic alpha into T adiabatic minus T adiabatic, right. And this alpha is basically the under relaxation parameter. Then you will go back to here and again calculate, right, because this is a new adiabatic temperature, then again compute the composition, again go through this all this process till you get this error. This is your error, okay. This error is the acceptable error, right. As I told, it is 1%, you are happy, fine. If you are happy with the 0.05%, right, you will have to go on doing that. That means it is the iteration in between iteration. This is quite complex. Are you getting the point? Okay. So now let us look at the, if you do this calculation for a propane air system at different equivalence ratio, you will get different things, right. For example, equivalence ratio 1, you will get water here and then CO2 this level, if I take this one, right, and of course nitrogen divided by this is not changing much, right. You will get CO values here and oxygen here, hydrogen here, right. Even if one at different each side you will get different values. Similarly you will get different values, like keep in mind that this corresponding to adiabatic temperature, you are getting maximum temperature, you will get 2278 Kelvin, phi is equal to 1.05, and this corresponding to 298 Kelvin and 1 atmosphere pressure, and these are all major species, okay. These are all major species, not radicals and other things. So we will be now seeing, if you do this thing, you will get various values like hydrogen, OH, O, NO, O values, all those values you will get. Now for that you can use several softwares which are available like Emkin, NASA CA and Cantera, and I was told this NASA CA basically is a free software. These are all you will have to buy. Chemkin and Cantera is free, where you can use MATLAB, Python kind of things. You know, it is a plug-in, you can plug in the thing, you do programming into it. There are several other softwares also available in internet. You please explore and find out, so that we can, you know, use this thing, right. Thank you very much.